Hello everyone, I am Shubhamkar Ayare. Sorry I'm not there in person today. I live in India, so it's a long flight to Europe. Plus, I'm planning to go for a PhD, so I'm going to be poor for the next few years. So, the topic of my presentation is py4cl2-cffi. We are using a particular implementation of Python called CPython. We are using its C API to enable calling Python callables from Common Lisp. So why do we care about interfacing with Python at all? Well, we all know that Common Lisp is awesome, and as much as we may dislike Python, we ought to acknowledge that its ecosystem is awesome. And I myself have a few invaluable libraries in Lisp. The Even then, the library count of Python vastly exceeds that of Lisp. And some libraries use C++ and do not even have a C interface. Thus, the goal of this line of work is to make it easier to prototype in Common Lisp. We should not be required to rewrite Python libraries in Lisp again. Now, there has been previous work on this topic. One is Burgle batteries. It aimed for a deep integration between Lisp and Python using CFFI and Python or C API. But it ran into problems related to signal processing, timeouts, floating point traps, and class inheritance trees. Lisp and Python can disagree on these things. A second approach is py4cl. It starts Python interpreter as a child process of Lisp and communicates with it using streams. It solves the problems faced by Burgle batteries, but it is extremely slow compared to using Python directly. A third approach is that of CLPython. It aims to provide a Python implementation written in Common Lisp itself. It solves both the problems. It can carry over the low-level peculiarities of the underlying Lisp implementation, and it also does not have any performance issues. But it faces a third problem. It does not have inherent access to CPython libraries, that is C extensions written for Python. This includes libraries like NumPy. So here comes py4cl2-cffi. Well, like Burgle batteries, we are using the C API of CPython, but we are only focusing on shallow integration. By using the C API, we do gain access to the C or C++ extensions of Python like NumPy. And our goal is to make it easy to call Python callables from Lisp. So we will convert between Lisp and Python objects, but we also provide a way to prevent the conversion. And we focus on other conveniences, other shallow but important integrations. This includes Lisp callbacks, handling asynchronous Python output, callable argument lists, and defining Lisp packages corresponding to Python modules. And where we do run into low-level disagreements, we try to use compatibility libraries like float features to deal with them. So a brief introduction to the CPython C API. Well, it's given in depth here. So if you are interested in this line of work or want to embed Python in your application, then you can check this out. For our purposes, the main C function we are concerned about is the py_object call. So py_object call can be used to call any Python callable. Now, what is a callable? Well, any object that can be called. Usually these are functions, but in Python we can also call classes or even instances of classes if the class implements a call method. So py_object call and its variants take in instances of a C struct py_object. While using from Lisp, we need to manage the creation and deletion of the instances of py_object. Each instance of the C struct py_object has a Python type and a reference count associated with it. We may wrap the py_object instance in an instance of a Lisp structure class py_object wrapper. So to sum up, we have in the C or Python world we have a py_object instance. In the Lisp or C world we have a pointer to that instance, and in Lisp we can create a py_object wrapper that that holds the pointer to the PyObject instance. The second important consideration while embedding Python is the global interpreter lock. Python interpreter is thread unsafe. Python requires the user to hold a global interpreter lock before doing even the simplest of operations. It can be held using the pygr state ensure and pygr state release. Both of these are C functions. But in Lisp we have macros, so we need not worry. We can create a wrapper py4cl2-cffi that wraps around CFFI foreign funcall. This provides a convenient way to call Python or C API functions. That is, we do not always need to remember to hold or release the GR. It will do so automatically. It also does a couple of other things, but this is one of the main tasks that it performs. Now, a number of things in the C API of Python are in terms of C macros, and these are unavailable to the Lisp system, which only has access to the dynamically loaded libraries. So the parts of the C macros that we do need, we put them in a Lisp utility library, as well as certain other helper functions, helper C functions. But how do we compile this how do we compile this C file? What header files do we use? Where do we find them? What compilation flags do we use? And even while loading the Python shared library, which other libraries do we need to load? Well, it turns out that Python has a helpful program called Python config. So we can find out which directly contains the header files, which LD flags to supply, or which libraries to load using Python config. So the end user only needs to ensure that the environment points to the correct Python or Python config programs. And py4cl2-cffi will call these programs using the UIOP run program and pass their output and set Lisp variables in the config package. It will then use these variables to embed Python appropriately. So coming to the most important task of calling the Python callables. So what steps are involved in calling a Python callables? Well, let's see an example of executing of calling the Python callable named str, which is the string function. It takes any object and returns a string representation of it. So given a callable name as a string, we want to retrieve the callable, that is a PyObject instance, corresponding to that name in Python. So there is this internal function pyvalue star. It takes in str, it takes in the name of the Python object and it returns a pointer to that object. We then want to convert the Lisp argument into PyObject instances. So this is performed by Pythonize. It takes an Lisp object and returns a pointer to the pointer to a PyObject instance corresponding to that object. Thirdly, we finally want to call the Python callable. So we have the pointer to the Python callable, and we have the arguments. We also perform some packing of the arguments into tuples and dictionaries, which is required by PyObject call and its variants. But we can call PyObject call using the py4cl2-cffi with its appropriate arguments, and this will return a pointer to a PyObject instance. This is essentially the return value. Now, finally, we want to convert this return value into a Lisp object. So this can be performed by Lispify. It takes in a pointer to a PyObject instance and returns the Lisp object corresponding to it. Now there are peculiarities involved in translating Python to Lisp types to Python types, particularly the nil. In Lisp, nil is overloaded. That is, it can also mean the Python value false, It can mean the Python value none, or it can also mean the empty tuple. In order to distinguish between these, we have two constants, py none and py empty tuple. These are assigned to the appropriate PyObject wrapper instance, which points to the none or the empty tuple. So from this in this table, uh, Lisp types, objects of Lisp type that are given on the left hand side are converted to Python types on the right hand side. So a vector in Lisp is converted to list, whereas a list in Python is converted to vector. A tuple in Python is converted to a Lisp list, or the object py_empty tuple. But different applications may have different needs. So the same type correspondence need not suit all. So type correspondence is customizable. So there are macros and variables with Pythonizers, and with Lispifiers and Lispifiers, which can help to customize how the type translation takes place. In addition to these, if the Python to Lisp type correspondence is unknown, then we wrap the Python object instance in an instance of the Lisp structure class PyObject wrapper. And if the Lisp to Python type correspondence is unknown, then we simply pass a unique integer handle from Lisp to Python. We store this integer handle in an instance of the Python class unknown Lisp object. And converting some objects can be costly. So the conversion can be avoided using the with remote objects macro. Additionally, there is a CFFI function called with pointer to vector data. This can be used to pass Lisp array data by reference. That is, we need not copy over the Lisp array data to Python. Unfortunately, we do need to copy over the Python array data, that is the NumPy array data, back to Lisp. But depending on your application, it may not be a problem. Coming to memory management, an instance of the C struct PyObject has a Python type and a reference count. The PyObject instance is garbage collected by the Python GC if its reference count becomes 0. Subsequent access of such an object can crash the Lisp program. So goals are twofold. One, we want to avoid program crash. That is, we want to prevent the Python object instance reference count from reaching 0 while Lisp is still using it. Secondly, we want to avoid memory leaks. So once the PyObject instance becomes inaccessible from Lisp, we want to deallocate it. So before discussing how we solve this problem, we discuss reference counts and kinds. In Python, there are two kinds of references. New reference, or the Python C API, has two kinds of references, new reference and borrowed reference. A new reference indicates object ownership. So a reference count is essentially the number of new references to the object. So once reference count reaches 0, the object may be deallocated by the GC. And secondly, there's borrowed reference, which does not indicate any object ownership, and the object may be deallocated even if there are multiple borrowed references to the object, but there are no new references to that object. So PyObject call returns a new reference to a PyObject instance. This we check whether this instance can be converted to a corresponding Lisp object. If we know how to do the conversion, we make the corresponding Lisp object and decrement the reference count of the PyObject instance immediately. So the PyObject is no longer needed, and Python GC can take care of it. If the correspondence is unknown, then we wrap the pointer in an instance of the PyObject wrapper. And we call trivial garbage finalize on this instance. And this finalizer we call pydecref on the PyObject instance. Then coming to convenience facilities. So for asynchronous Python output, the problem we face is that different Slime or Emacs buffers have different standard output. So in default state, when Python sends output to Lisp, it appears in the inferior Lisp buffer. A solution to this is to let Python send the output to a named pipe. A Lisp thread reads output from the named pipe and sends it to standard output. And the Python output can now appear in an appropriate Emacs buffer. Then there's def by fun. It takes in a callable name and a module name, and it defines a list function, list fun name, to call the Python callable given by callable name and Python module name. So if we check the macro expansion of this, it roughly expands into import function statement and a pycall statement, an import function form and a apply pycall form. The import function form is important because in case the Python interpreter is reset, well, there's a particular way in which we do reset the Python interpreter. That is, we delete all its global variables except for a few important ones. In those cases, we want to re-import the modular function again, and the import function form does exactly this. Once that is imported, pycall can take place. Then there's def by module. It takes in a Python module name and optionally an import submodules, and it defines a Lisp package or multiple packages which hold Lisp functions that call appropriate Python functions, Python callables. So for example, if we check expansion of def by module math, it roughly expands into a def package form and a number of different forms corresponding to each Python callable. Well, coming to performance, which is one of the most important aspects about why we went from py4cl2 to py4cl2-cffi, we note that there are for the particular task at hand, converts an integer to a string, and for this task we have the most generic pyobject call, and it's also the slowest. But we also have the most specialized and also fastest for the task at hand, pyobject str. Both of these are C functions. So we compare performance in terms of code that calls these functions. So on the particular environment that I ran code in, I tested the performance in. Python runs at about 1,000,000 to 1,500,000 instructions per second. Pycall.gl, which is a Julia library to call Python, to use Python libraries, it runs at about just 3 times slow. But over in Lisp, the performance disparity is still significant. Whereas Burger batteries and py4cl are slow, and the py4cl2-cffi is faster than them, about 3 to 10 times as fast, but it is still another order of magnitude slower than pycall.gl. So there's plenty of scope for improvement. So these improvements could include finding the Python object corresponding to a particular name at compile time itself. It could also include avoiding the dispatch on Lispifiers and Pythonizers, and maybe there are other optimizations that I haven't yet explored. So coming to limitations and future work, well, we are currently limited to x86 64 hardware and Unix based OS. So there's a branch called Mac OS which is still which is still a work in progress, but porting to Windows remains a far-fetched dream. So handling case sensitivity is also work in progress. Performance issues, yeah, there's plenty of scope for improvement. Then there's floating point traps. I have run into floating point traps, but signal handling is I haven't yet run into signal handling issues, mainly because I haven't tried it. Then there are so certain libraries like matplotlib, in their default settings, do not like to play nice with multi-threaded environments. That is, they want you to call the plot function only from the main thread. So again, making a version of py4cl2-cffi that only uses a single thread to communicate with Python is another work in progress. So to conclude, we can use py4cl2-cffi for basic tasks. For MMac, MStarMac, it is work in progress. We can also use NumPy. Then multi-threaded compatible libraries, we can use them. Matplotlib, well, it is a work in progress. So for MStarMac, there's a macOS branch, and for Matplotlib, there's uh, you can either configure Slime or your IDE to use a single thread, or you can use the experimental system py4cl2-cffi single threaded. So finally, I would like to thank Marco Hezek for developing Clappy. So py4cl by Mendelssohn was actually based on Clappy. Both of these use stream-based communications, and this has eventually led to py4cl2-cffi, and there have been lots of other people who have contributed to each of these projects. I also want to thank them. All right, thank you. I'll take my leave. If you have any issues or if you have any questions, you can raise the issue,
So
send me an email, or
I think
yeah,
we're
we
set up to
can
do some
just have a chat.
questions. So,
Hello everyone, I'm Shubhamkar Ayare. Sorry I'm not there in person today. I live in India, so it's a long flight to Europe. Plus, I'm planning to go for a PhD, so I'm going to be poor for the next few years. So, the topic of my presentation is py4cl2-cffi.
did you mention, is it in Quick Lisp yet? That's my question, and then I'm ready to hand it over to anyone with any.
Uh, I couldn't hear the question. Could someone repeat?
Do you is this in Quick Lisp yet?
Parfus, I think yes, but it will be an older version because in recent months, lots of news has taken place. Uh, Ultralist, I think it is an Ultralist, but I will double check. Yeah, so up by ELS, you can try it out. Yep.
So, any other questions? Yeah, Marco's asking a question. Take both. Yeah.
So thank you for the talk and also for politely giving credit for this half day of work that I put in originally into this Python bridging. So my question is so this performance gap that still exists. So let's say what Julia can do or other interfaces. How much do you know about how that goes missing? Is that the trampolining into SPCL, or where is the performance being lost right now?
So currently, okay. So as far as I understand, Julia, it has amazing just-in-time compile facilities. So this means once it receives arguments, it can process those arguments and prepare a optimal function corresponding to those arguments or the types of those arguments. Unless we need to do that process manually. So here there are three steps. One is so there are three generic steps involved. One is fetching the PyObject instance from the name of the PyObject or the from the variable name, that is, let's say the str, we from the name str or from the string str, we need to fetch the string object. This currently it is being done at runtime, but we could do it at compile time using compiler macros. Secondly, Pythonize and Lispify both are generic functions, so they too are performing runtime dispatch. Again, if we could do the dispatch at compile time, I think we might obtain better performance. But beyond these three, if there are other performance issues, then I still need to check them.
Any more? So they seem satisfied.